So in the previous lecture, we learned the basics of probability theory. Now we understand about probabilities and so on. Well, today we're going to focus more specifically on probability distributions of random variables. So for example, remember last time we had some experiments where we flipped an ordinary coin and we counted the number of heads that we had. Well, let's think about that a little more. So if we flip the coin twice in an experiment, and if we let y be the number of heads, then we already worked out the probabilities. We said the probability that y equals 0 is a quarter, the probability that y equals 1 is a half, and the probability that y equals 2 is equal to a quarter. These numbers add up to 1 and they give us all the probabilities for the random variable y. This is called a probability distribution. And in this case, it's called the binomial 2.5 as the distribution. So this is a particular name that we give to the distribution. It means we did 2 experiments. In this case, we flipped the coin twice. And the probability of success or a head each time was equal to a half. For something even simpler, if we flip just one coin and let x be the number of heads, or we could say it's just 1 if it's a head or it's equal to 0 if it's a tail, then we can say, well, the probability that x equals 1, that's the probability we got a head, so that equals a half, and the probability x equals 0 is also a half. So we could call this the binomial 1.5 if we wanted. We also call this the Bernoulli a half as a distribution. And this means, it's a special name to mean we just did one experiment and the probability of success, or 1, was a half. Otherwise, we get 0. If we imagine flipping a coin 3 times, then the calculations get a little bit trickier, but it's still not hard to work out the probability distribution. Again, if we let x be the total number of heads that we get, then x could be 0 or 1 or 2 or 3 with these probabilities. And this would be called the binomial 3.5 as a distribution. So we see in this way that as we flip more coins, we get all different sorts of distributions. Or if we imagine flipping those bottle caps like we did last time, well, suppose we knew that the probability of getting red on each bottle cap was a third. In that case, if we flip one bottle cap and count the number of reds, then that would be the Bernoulli 1/3. Or if we flip the bottle cap twice and count the number of reds, then that would be the binomial 2/1/3. And we can work out the probabilities for that as we did. The probability that the number of reds equals 0 or 1 or 2. For a whole different kind of example, we can imagine rolling a 6-sided die like I have here. Well, if I randomly roll the die and let one particular side show, in this case I got a 2, well, I was equally likely going to get any of the numbers between 1 and 6. So we can set this up as saying that if you roll one die, and if you let W just equal the amount that's showing on the die, then W is equally likely to be 1 or 2 or 3 or 4 or 5 or 6. Each probability is equal to 1 out of 6. We can call this the discrete uniform distribution, which is to say the probabilities for W are uniform, equally likely on the 6 points, in this case the numbers from 1 up to 6. Now, once we're talking about these random variables, we can talk about other quantities related to them. For example, we can talk about their mean or their expected value, which is what number they equal on average. There's a simple formula for computing the expected value of a random variable x. You just add up all the possible values multiplied by all the probabilities that x equals that value. So for example, if we're rolling the die and looking at the number shown, then the mean would be equal to, well, 1 multiplied by a sixth, plus 2 multiplied by a sixth, plus 3 multiplied by a sixth, and so on up to plus 6 multiplied by a sixth. This works out to 3.5, not 3 as some people might think. So we say that on average, if you roll a die, the average or mean or expected value that you'll get is equal to 3.5. If we go back to that coins example, we can say if we flip 2 coins, Well, we might get 0 or 1 or 2 heads, but we know the probability. So the expected number or mean number of heads that you get when you flip 2 coins would be computed as 0 times a quarter plus 1 times a half plus 2 times a quarter, which works out to 1, which is what you might have expected. Okay, so now we understand the mean or expected value of a random variable. There's another quantity that we need to understand too, and that's called the variance. Now you may recall in last week's lectures we talked about the variance from some data from a sample, but we also have the variance in the theoretical world. In this case, the variance again tries to measure the spread of the values, or how far away they tend to be from their mean value. The formula is a little bit more complicated. It's given as follows. We take a sum of all the squared differences between the value and its mean and multiply that by the probability. So it's the expected value of how far the random variable is from its mean squared. So for example, if we just flip one coin, and if x is 1 if it's a head or 0 if it's a tail, well, then we can work out the variance because we just compute it as being 1 minus a half squared times a half plus 0 minus a half squared times a half, which works out to a quarter. We also have the standard deviation, or SD, just like in the experimental or real world, and the standard deviation is just the square root of the variance. So in this case, the standard deviation is a half. We could also consider, say, when we rolled that 6-sided die. In that case, we know that the mean was equal to 3.5, and now we can compute the variance by taking, well, 1 minus 3.5 squared times a sixth, plus 2 minus 3.5 squared times a sixth, and so on up to plus 6 minus 3.5 squared multiplied by a sixth. And when you work that all out, you get it to be a certain number which works out to about 2.92. And then the standard deviation is the square root of that. So in this way, we can compute not only the mean, but also the variance and the standard deviation of a random variable. Now, these quantities satisfy a few simple properties. The mean, or expected value, satisfies the nice property of being linear. It means if we take any linear combination of two different random variables, say x and y, then the expected value is just the corresponding linear combination of the individual expected values. This will turn out to be helpful to us later on. The variance is not quite as good. If we take the variance of, say, a constant multiplied by a random variable x, then the variance multiplies by a squared. And if we then take the standard deviation, well, it multiplies by the absolute value of a. So if a is positive, it just multiplies by a, but if a is negative, it multiplies by the absolute value, or the positive part of a. If we add a constant, that doesn't affect the variance. So the variance of ax plus b is just a squared times the variance of x with no mention of b. Now the variance of a sum of random variables, variance of x plus y, sometimes it equals the sum, the variance of x plus the variance of y, but only if x and y are what's called independent, that they don't have any special influence over each other. We'll come back to that point later. So far, all of these random variables that we've been considering are what we call discrete random variables. It means that the possible values they take are values that can be written in a list. So maybe they can be 0, 1, or 2, or maybe they can be 1, 2, 3, 4, 5, or 6. But they're just values which we could write in a list. What if we had a random quantity that could take any value in a whole interval? This is called a continuous random variable. The simplest example of a continuous random variable, or a continuous probability distribution, is uniform on the interval from 0 to 1. Now this means we have a random quantity which is equally likely to be anywhere in the interval 0, 1. Well, it's a little harder to pin down what this means. We can think of it in terms of the probability that this random quantity is in any interval within 0, 1. For example, the probability that this random quantity is, say, between 0 and a third, Well, that should be a third because that's the length of that interval. Or the probability it's between, say, a half and 3/4 should be 3/4 minus a half, or a quarter, because that's the length of that interval. And in general, the probability that it's between any two numbers a and b should be equal to b minus a whenever a and b are within the interval. Now this has an interesting consequence. It means that the probability that x equals any particular number a is equal to the probability x is between a and a, which is a minus a, which is 0. So it means somehow with probability 1, x will be somewhere between 0 and 1, and yet the probability is 0 that x equals any particular value. This is a little bit confusing, and we've learned that it's best to think about a continuous distribution like this, not by keeping track of all the individual probabilities, but by thinking of it as the area underneath a graph of a function. This function is called the density function. And for the uniform 0-1 distribution that we've been considering, the density function is a function which equals 1 in between 0 and 1 and equals 0 everywhere else. Then we can talk about probabilities as being the area underneath the graph of this function. So for example, the probability that this random variable is between a half and 3/4, well, we can think of it as the shaded area here, the area underneath the graph, which is in between a half and 3/4. And of course, that area is equal to 1/4, as we already figured out. Now, once we understand about density functions, then we can use them for other distributions too. For example, instead of just having a random variable that's uniform between 0 and 1, we could have a random variable that's uniform between, say, 10 and 50. It would have a density which is equal to 1 over 40 for all numbers in between 10 and 50. Otherwise, it's equal to 0. And the total area under the graph is still equal to 1. But now we could say, oh, the probability that the random variable is, say, between 25 and 32, well, would be given by the area underneath the graph, which is between 25 and 32, which in this case is equal to 7 out of 40. Other density functions will give us other examples of continuous probability distributions. For example, the exponential 1 distribution has a density function which is equal to e to the minus x whenever x is a positive number. Otherwise, it's equal to 0, as shown here. And again, the probability that, say, that random variable is between 2 and 3 would be equal to the area of the shaded region, which is underneath that graph. The single most important continuous distribution that we're going to study is something called the normal distribution, or the Gaussian distribution, or sometimes called the bell curve. And it's got a density which is given by this strange formula here. It's given by 1 over the square root of 2 pi times e to the minus x squared over 2. Now that's a function whose graph looks like this. And again, the total area underneath the graph is equal to 1. And again, the probability that, say, this random variable is between, say, a half and 1.5 would be given by the area underneath this shaded region here. And once we have one bell curve that we like, well, we can make other ones by shifting them over. And what's called the normal mu sigma squared probability distribution is just given by starting with that old standard normal distribution and then shifting it over by some amount mu and stretching it out by some amount sigma. So for example, the normal 3, 2 squared probability distribution would be a bell curve which is centered at 3 and which is stretched out twice as wide as compared to the original standard normal curve. So in this way, we have lots of different probability distributions. One nice fact is if we have a random quantity, say x, which has the probability distribution given by a normal mu sigma squared for some mu and sigma, then we can standardize it by subtracting off the mean and dividing by sigma, and that gives us a new quantity z, and we can see that z will then have the standard normal distribution, also called normal 0, 1. So there's relations between all these different kinds of continuous distributions. The last thing we need to realize is that just like for discrete probability distributions, continuous distributions also have a mean and a variance. Now, in this case, computing it is a little trickier. We have to compute an integral instead of a sum, which may be scary for some people. So in this course, we're not going to worry too much about it. But for example, if we had a random variable which was uniformly distributed on 0, 1, then the mean would be the integral of x dx from 0 to 1, which is a half, which is what you might expect. And the variance would be, well, x minus that mean of a half all squared, and then integrate that from 0 to 1, and that works out to 1/12. For the exponential 1 distribution, the mean is a formula in this case, which is the integral of x times e to the minus x, taken from 0 to infinity, because that's all the possible values, and that works out to be just 1. And in this case, the variance, which is again an integral, also works out to 1. For the normal distribution, well, it's hidden right in the notation that if it's normal 0, 1, then the mean is 0, and the variance and standard deviation are both 1. If it's normal mu sigma squared, then the mean or expected value is mu, and the variance is sigma squared, and the standard deviation is sigma. So we don't need to worry too much in this class about how to compute those integrals. We just need to understand that there's all sorts of different probability distributions. There's discrete ones and there's continuous ones, and they all have means and variances and other properties that we'll learn more about as we go forward. In particular, we'll learn that that normal distribution will turn out to be the most important distribution for us. We'll see that in the next lecture.